Hey guys, I hope everyone's having a great day. Mr. B here. And today we're going to talk about momentum. So, um, basically, I want you guys at this point to think about maybe times you've heard this word used. Maybe you're a sports fan and you've heard, oh, this team has all the momentum in their direction. Or maybe you're thinking you're doing something yourself and you think, oh, I've got to get momentum going my way. But what do we mean by momentum? So, whether you meant it in that way, non scientifically, or in a scientific sense, it almost kind of means the same thing. Okay, if something has momentum, something has a lot of momentum, it means it's kind of difficult to stop. Okay, the more momentum an object has, the harder it is to stop. And now this sounds a little bit like a word we had learned previously. If you remember Newton's first law, also called the law of, I'll give you a second. That's right, inertia. And if you'll remember, the inertia of an object is how difficult it is to change its motion. And that was dependent on the mass of that object. Something with a large mass was difficult to change its motion. Something with a smaller mass, not quite as hard. Okay, so momentum just a little bit different. Momentum is how difficult it is to stop a moving object. Inertia can refer to an object in motion or an object that is at rest. When we talk about momentum, we assume that that object is already in motion, and our purpose is to try to stop it. Okay, but momentum isn't a vague concept. It's actually a very specific, measurable thing. Okay, but before we get to the measuring part, let's do a mental exercise. All right, so think about this, guys. We just said that the more mass an object has, the more inertia it has. But let's think about this now in terms of momentum. The more mass an object has, the more momentum it has. So it's similar in that way. Would you rather try to stop a baseball going at 20 meters per second or a truck? I'm hoping everybody said baseball, because if you said truck, we might have to talk. But there's a reason that baseball is the answer here, because baseball has much less mass than a truck, and you'd have a reasonable chance at stopping that baseball just by catching it. A truck, on the other hand, not so much, and it's purely because of the mass. The velocity is the same, but the mass of the truck will make it a lot harder to stop. But unlike inertia, momentum is also dependent on the velocity of an object. So, just like mass, it has a positive relationship. The more mass the object has, the harder it is to stop. The greater the velocity, or the more velocity the object has, the harder it is to stop. So you can imagine something with a very large mass going very fast would be extremely difficult to stop. Whereas something going at a very low rate of speed or a slow velocity that is small in mass, much, much easier to stop. Okay, so I told you that momentum is a very specific, measurable thing. So how do we go about making this measurement? Well, first of all, we have to know what we're measuring and how we are coming about this measurement. So first of all, momentum is represented by the lowercase letter p. I believe we talked a little bit about this in class, about how sometimes the things we use as abbreviations in math and science don't make sense with as far as the language goes, but these abbreviations come about in many other ways, not just by the letters contained in the word. So anyway, lowercase letter p, that's going to mean momentum. The two things we're going to need to solve momentum are mass and velocity, represented by m and v respectively. Important to note here, guys, that mass and velocity have to be in the correct units. Your mass needs to be in kilograms, your velocity needs to be in meters per second. Okay, if it's not in those units, your calculation is going to look kind of funny. And when you multiply those two out, mass and velocity, you end up with your momentum. And the units for momentum are kilogram meter seconds. I know that's a mouthful, but that's what the unit is because we're literally multiplying kilograms and meters per second. So not a lot of imagination going on there, but those are the units we use. And please remember, guys, that when you do these calculations, to please put your units, because just numbers alone don't answer a question. Now, right now, what you're seeing on this on the picture here is a triangle with all of the different factors you need for this equation. The reason it's presented in this triangle is to show you a little device that makes it a lot easier to rearrange this equation. Okay? If you think of the horizontal line, that is the line going through the center of the triangle that divides it into a triangle up top and two other shapes at the bottom. Okay, think about that as a dividing line. And think about that vertical line in the middle that doesn't quite go to the top of the big triangle, the line between the M and the V. Think about that as a multiplication sign. Okay, M times V is what gives you P. P over V will give you M, and P over M will give you V. So depending on what the problem is asking you, you may have to rearrange the formula. If you're given any two pieces of information, you should be able to solve for the third. And if rearranging formulas is something that's given you trouble in the past, this is a good little device for simple multiplication equations. It's made life a lot easier for me. And when I take a test, sometimes if I'm using a simple concept like this, one of the first things I'll do is write out the triangle, just so I don't have to think very hard about how to rearrange that formula. So as we said, momentum is equal to mass times velocity. Or if we wanted to use the shorthand version, P is equal to M times V. So we're going to get into a practice problem here. How much momentum does a 400 kilogram bike moving at 40 meters per second have? And this is simplicity itself, right, guys? All we do is we replace the letters with the numbers that we know. We don't know P, that's what we're solving. But in the problem, we're given M, we're given the mass of the bike. We are given the velocity. The mass is 400 kilograms. The velocity is 40 meters per second. First thing we really should do is ensure that they're in the correct units. Mass is in fact in kilograms. Velocity is in meters per second. So we're good to go. We just multiply it out and we end up with 16,000. But you know what? I ask this question all the time when we do a calculation like this. If I write down 16,000, am I done? And I'm hoping more than a few of you are shaking your head no. No, we are absolutely not done. Because you see in that little box there are our units. That's actually what makes our answer mean something. That's in fact what tells us something. If you just put 16,000, the first thing I'm going to ask, even though I know just by looking at the problem, the first thing I'm going to ask is 16,000 what? And by putting the units, you're answering that question. Okay, we're going to do a couple of sample problems, guys. So let's take a look at the first one. And I really like this problem because this really is more like a problem you'll see in the more difficult section of a test. But which has more momentum? A 3 kilogram sledgehammer swung at 1.5 meters per second, or a 4 kilogram sledgehammer swung at 0.9 meters per second? Just looking at the problem, something tells me it's going to be pretty close. But the only way to know for sure is really to calculate it out. So let's do one at a time. The mass of the first sledgehammer, 3 kilograms, we're given that. The velocity is 1.5 meters per second. So that's enough information to calculate the momentum. If we multiply 3 times 1.5, by the way, I forgot to mention, we should do that little obligatory check to make sure that everything is given in the right units. And the mass of both hammers is in fact in kilograms, the velocity in meters per second, so we're good to go. For the first one, we have 3 kilograms, 1.5 meters per second. Multiply those out, you end up with 4.5 kilogram meter seconds. All right, let's take a look at the second one. The mass is 4 kilograms. The velocity is 0.9 meters per second. When we multiply the mass and velocity out, that's 4 times 0.9, we end up with 3.6 kilogram meters per second. All right, so we can see very clearly then that hammer 1 has more momentum. Okay, we're going to move on to a concept now called conservation of momentum. Okay, and the law of conservation of momentum is very similar to another law of conservation of that we had heard before. Okay, remember we talked about the law of conservation of energy? I'm going to give you just a second to think about the wording of that law. If you thought energy can neither be created nor destroyed, only change forms or be transferred, you would be absolutely correct. And I am totally proud of you because remember I told you, if you don't remember anything else I teach you this year, please remember that. But basically any law of conservation of is going to have very similar wording. And the law of conservation of momentum refers to objects that have collided with one another. And the law basically states, with the absence of any other forces outside, the total momentum of the two objects is the same both before and after the collision. Okay, so in other words, the momentum is conserved. It might be redistributed a little bit, but the total momentum is in fact conserved. And again, I want to point out, guys, that this is under the assumption that that there are no other forces and there are no other energy transfers out of that system. It's a closed system. So we're going to make that assumption when we do any calculations about the law of conservation of momentum, is that every bit of energy, every bit of momentum is conserved. Okay, friction would be an example of an outside force that would change our numbers. So for the moment, when we do these calculations, as I said, we're going to pretty much pretend that friction doesn't exist. As you go up in levels and you go into high school physics and college physics, you're actually going to learn how to factor this into your equations and how much friction will actually take away from that system. But mathematically, this is what it looks like. So we have one object, P1, or the momentum of one object, P1, the momentum of another object, P2. If we add those momentums together, and then those objects collide in a closed system, the momentum of object 1 plus the momentum of object 2 after the collision should be exactly the same. And we represent momentum of object 1 and momentum of object 2 the same way as in the initial equation, P1, P2, but we put a little comma after each one, and we say P prime, P1 prime, P2 prime, meaning the momentum of object 1 and the momentum of object 2 after the collision. Okay, so if we were to say this mathematically, it's P1, the momentum of object 1, plus P2, the momentum of object 2, is equal to P prime 1, the momentum of object 1 after the collision, plus P2 prime, the momentum of object 2 after the collision. But what that means, guys, is that if you break down momentum, momentum itself is m times v, right? So if we took the momentum and velocity of object 1, we of course get the momentum, but if we add that to m2v2, the momentum and velocity, the mass and velocity, I think I said momentum for the first one as well. It should be mass. The mass and velocity of object 2, it should be equal to m1v1 prime, and I'm sorry, but the prime symbol is missing from the second set here, plus m2v2 prime, or the mass and velocity of objects 1 and 2 after the collision. What does that look like? Okay, so take a look at these guys here. So you have a truck that is 3,000 kilograms going at a velocity of 10 meters per second. You have a little car that's 1/3 that mass, 1,000 kilograms, and it is absolutely still at 0 meters per second. This is the before. The after, well, nobody's happy in the after, particularly the guy in the smaller car, But we see there's been a redistribution of things. The masses don't change, but the velocities will, because when we multiply them out, we have to get the same momentum combined as we did before. So let's do the math here. If we calculate the momentum of the truck, 3,000 times 10 gives us 30,000. For the car, 1,000 times 0, anything times 0 is 0. So 30,000 times 0 gives us 30,000. And what were those units again, guys? That's right, it's kilograms, meter seconds, or kilogram meters per second. All right, let's go to the second one. We don't know the velocity of the truck after the collision, but we do know the velocity of the car now, which wasn't moving at all. So we'd find out the velocity of the car, which would be 1,000 times 15. That gives us 15,000. We know that the combined momentum has to be 30,000 because it was before. So what would we have to multiply by 3,000 kilograms to get 15,000? I'll give you a second to try to figure that out, guys. That's right. It is 5 meters per second. So now we know that the truck is going at 5 meters per second after the collision because I'm giving you a second to word it yourself, because momentum has to be the same before and after the crash. Now, in real life, both of those vehicles are eventually going to slow down and stop because of friction and gravity and maybe other forces that are applied. But for this purpose here, we're purely looking at that moment of impact and how momentum is totally conserved. And we're going to finish up here, guys, with just a thought. All we've talked about so far is momentum for an object traveling in a straight line. Okay, but objects quite often don't just travel in straight lines. Sometimes we take a circular course or a parabolic course or something with some degree of curvature. And that is known as angular momentum. Now, it's a little bit more of a difficult calculation, and we're going to go over that in depth when we talk about angular momentum after our PMA review. So guys, I want to thank you for your attention. I hope you got enough out of this to be able to do the calculation worksheet. Remember that after this was the I do section. The you do is your calculation worksheet, which must be turned in. The we do is a discussion board where I'm asking you to answer the question and then comment on two of your classmates' comments. I would appreciate it, guys, if your comments were nothing but encouraging and supportive. And, of course, the language was, as always, school appropriate. Guys, I hope you have a great day, and I will see you on Friday. Take care, everybody.